Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see here. In this video we'll talk about the 8-bit increment module, which you can see here. And in this CPU there are two of such modules, and together they form the 16-bit increment unit used for incrementing the program counter to prepare for the next instruction. Now how this works in detail is not shown here, but it's a subject of another video, so please watch that. However, in this video we'll take a look at this module and see that it is constructed out of 8 half-adders. We'll take a look at how a half-adder works, how it can be constructed out of gates, how it can be cascaded to add 1 to a binary number. And finally we'll take a look at how a half-adder works on the breadboard and also how part of this module works. In other words, how to add 1 to a binary number. So, a half-adder is basically a block that looks like this. It has a carry in input, it has an A input, a Y output and a carry out output. We'll get to what all this means in a second. Now A and carry in are basically interchangeable. This could be named B, but for the sake of cascading this, it makes more sense to name this carry in, because we will see that the carry in and carry out of two subsequent half-adders are connected together. So Y is basically the sum of A and carry in modulo 2. Obviously modulo 2 because there's only one bit, so there's not much more will fit into one bit. Carry out is well, the carry, so if the sum of A and carry in doesn't fit in Y, carry out will be 1. Yeah? In this plugin module, the half-adders are cascaded like this. So the carry out of a module is connected to the carry in of the next module, and so on. All the inputs A together form a binary word, X. In this case it's 8 bits wide. This will be the least significant bit, and the most significant bit will be all the way down. The outputs formed by the binary word formed by the outputs Y is another binary word. Is a result, actually. So in case the carry in is 0, the output, so that is a sum of the input plus 0, would simply be the input. So that's not a very interesting case. Now if carry in is made 1, the output is the input plus 1, and that's exactly what this module does. So it has an array of 8 inputs which form a binary number, the input number. It's half of the address actually in context of the CPU. It has a carry in input for cascading two of these modules together, right, because there are two. And well, it has an output which is also a binary number, which is used as the next program address. Yeah, let's take a look at how adding numbers works, or rather how adding 1 to a number works. Let's say we have a number X, which is 10100, and let's say we want to add 1 to that, and we're doing that in a binary system. So this 1 corresponds to this 1 as the input to this whole module. 1 and 1 modulo 2 is 0, carry a 1, 1 and 1 modulo 2 is 0, carry a 1, 1 and 0 is 1, carry 0, 0 and 1 is 1, carry 0, 0 and 0 is 0. So the result would be this, which is exactly X plus 1. And this number is of course this number. These bits correspond to all the intermediate carries between half-adders. They're not interesting, they only exist within a module. They're not coming out of it, or not going into it. So let's recap what a half-adder does. Y is a sum of A and carry in modulo 2. The sum of both of its inputs modulo 2. Carry out is the, well, if the sum doesn't fit in Y, carry out is being made 1. So let's write a truth table of a half adder. Inputs A and carry in, outputs Y and carry out. It's not too difficult. Right, Y is a sum of both inputs modulo 2. So 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, 1 and 1 is 0 modulo 2. And if that happens, the carry out is set to 1, because it doesn't fit, the result doesn't fit in Y anymore. In all other cases, carry out is 0, right? So how to make this using gates? Our carry out is very simple. You see, this carry out is simply A and carry in. So let's draw that. A and carry in. Simple AND gate, carry out. Y is, what you see here is an XOR function. So Y is 1 if one of A and carry in is 1, but not both. Let's avoid the XOR function. Let's write that exactly as pronounced. Output Y is true if either A or carry in is true, but not both. Right, like that. Now, one rule of Boolean logic is that A and B, so A and B are both true if it is not the case that either A or B is false, right? So you can transform this into this. So we can transform this into this. Negate each term and negate the complete term. So not and not cancels, so we can remove that. And now it's a bit simpler, because A and carry in is exactly carry out. So we can replace that with carry out. So what you see now is a NOR function of A and carry in, right? And the result of that NORed with carry out. Now we can draw that here, namely one NOR there, and the result of which is NORed again with carry out to form Y. So this is a half adder made using discrete gates. Now let's take a look on the breadboard how a half adder behaves. And in order to do so, you want to take a look at both of its inputs, namely A and carry in, and both of its outputs, namely Y and carry out. However, within this module, not all of these pins are accessible. As you can see, let's take the very first half adder in the chain. So this is the least significant bit in the module, so to say. In other words, this carry in is available. That's an input to the whole module. This A is also available. That's an input to the module. This Y is also available as an input to the module. However, this carry out and this carry in is a track on the PCB. It's not, well, you can solder to it, but it's not easy to, it doesn't come out of the module using a header pin. So what we can do instead is simply make this input 0. So whatever comes in at this carry in input will be output to the Y output. Because the sum of something with 0 always fits on one bit, and that bit simply comes out here. So let's do that on the breadboard, and for that we will use the CPU as a table again. This is the breadboard in question. This is the module in question. Let's plug the module into the breadboard like that. Ooh, yeah. I'm gonna put it aside now. We have wires clipped to clipped to these nodes actually, these 4 nodes. And for convenience, I'll use this. Okay, we'll use this box again to display all those nodes. So this is all the pins of a half-adder. This is input A. The second one from the right is input carry in, output Y, output carry out. As you can see, if we make input A or carry in high, by the way, LED off means low voltage means 0, and LED on means high voltage or 1. If you make either A or carry in high, the output Y is high. So it doesn't actually matter which one. Now if we make both A and carry in high, we see that carry out is activated and sum modulo 2 becomes 0. So that's exactly how a half-adder works. Now for so that's how a half-adder works. Now let's take a look at 2 bits of this board. So let's consider a binary number consisting of 2 bits, and let's vary this carry in. Let's first make it 0 and then make it 1, see what happens, and let's take a look at this output consisting of 2 bits. So 2 bits go in, 2 bits go out, and we'll play with this carry in. In order to do that, I have to change something on the breadboard, because we don't need that anymore, so we'll do it like that. First we make the carry in 0. Right. Use that as a table again, and let's put a bit of tape on it again so that it's clear which is which. There we go. Right. So the rightmost 2 bits are 2 bits of input A. So the first 2 bits of the module, basically. The rightmost bit is the least significant bit. That is bit number 1, that is bit number 0 of the input. And likewise, the 2 leftmost LEDs and 2 leftmost switches, but we don't use them now, are the least significant bit and bit 1 of the output. So, and this is the case where carry in of the whole module is 0. So basically we're adding 0 to the input word, and that's exactly what we see now. So input is binary 0 and the output is also binary 0. So if you make the input 1, binary 1, the output is also binary 1. If you make the input binary 2, the output is also binary 2. So make the input binary 3, I can see it easier, and the output is also binary 3. So this is very boring, yeah. So now let's make the input carry, the carry in of the whole module 1. Immediately see that if the binary word as input, the input is still 0, binary 0, and the output is now 1, right? If you make the input binary 1, the output becomes binary 2, because bit 1 is 1 and bit 0 is 0. Yeah? So if you make the input binary 3, the output would be binary 4, except we're only showing the first 2 bits, so those are 0. So this is actually the function of the 8-bit increment module within the CPU. That's the actual function, to simply add 1 to the input. But that's how it works actually. When cascading this module, because there are 2 of these modules in the CPU, the carry in of the first module will be made 1, because we're adding a constant 1 to whatever comes in, and the carry out of the first module in the chain is connected to the carry in of the second module in the chain, and the carry out of the second module is simply discarded because there are only 2 modules in the CPU. So what these do together is add a constant 1 to a 16-bit number, which conveniently is the program counter. So that's how it works basically. Thank you for watching, and let me know what you think. If you're interested, please watch the other videos, and for more information check out the Qibec site, which is qibec.org. Thanks for watching, have a nice day, and goodbye.